Today, we're going to continue our journey of solving equations by reading the expression and then doing inverse operations in reverse order. This is just a play on the do the same thing to both sides of the equation to maintain balance idea. It goes into a little more detail because we want to look at what order we should do things and how we should, and that's the read the expression part. So we want to incorporate reading an expression properly so we can decide what to do to solve. This will also build our skills in determining what the inverse of a function is when that comes up. So let's remind ourselves of the important things that we've talked about so far in solving equations. We know that that addition and subtraction are inverses, and we also know that multiplication and division are inverses. That left us with exponents. We had three operations: addition, multiplication, and exponents. The inverse of an exponent is a reciprocal exponent. So if we want to solve x to the third is equal to 7, then the inverse operation is that x is raised to the 1/3 power. So x to the third equals 7. That means x equals 7 to the 1/3. And if it's not a radical that we recognize, then we are going to have to use our calculating machines or just write the cube root of 7. So in this case, 7 to the 1/3 power is 1.913, we'll call it, rounding to the nearest thousandth, as is our way. So 1.913. This is an approximation to the nearest thousandth. So this is the approximation of the answer. If we had an equation involving an exponent, let's say x to the 3/5, and that equals 7, then the inverse operation is a reciprocal exponent. So to solve, we would write x would be 7 raised to the reciprocal of the exponent on x, 5/3 power. And this is just a calculator exercise as well. So now I just want 7 to the 5/3, and that's just going to be the 5th power what we had before. So 25.615. Once again, once we hit enter on our calculator, we are looking at an approximation, unless the digits stop. So the inverse of an exponent is a reciprocal exponent. Also, these fraction exponents are radicals. Radicals are fraction exponents. So a radical is a fraction exponent where the index of the radical is the denominator of the exponent. The index of the radical is the denominator of the exponents. So we really want to get the idea that when we see radicals, we should see them as fraction exponents. So if I wanted to solve an equation, for example, if I had an equation that said the 5th root of x is equal to 3, we're going to read the 5th root of x as an x to the 1/5 power, where the index of the radical is the denominator of the exponent. So this is going to be an x to the 1/5 power. The reason that we want to read the radical as an exponent, as a fraction exponent, is that when we want to solve, the inverse of an exponent is a reciprocal exponent. So to solve, we could say that x is equal to 3 to the 5th power. So instead of a 1/5 power, you raise the reciprocal, which is 5/1. So 3 to the 5th. So we can raise 3 to the 5th power and get 243. Here, the decimal stops, so this is an exact value. So lucky us, we don't have to round to the nearest thousandth. This also means that we can use radicals to solve our equations. So going back to our first equation, where we had x to the third equals 7, we can also write the solution in radical form. So if x to the third is equal to 7, we can also solve this equation by doing, since it's a 1/3 power of 7, we can write that as the cube root of 7. So we could say x equals the cube root of 7. And then if we need an approximation, we can just go to the cube root of 7. And it's still 1.913. To change notation, we shouldn't change the value, otherwise something has gone horribly wrong. So one of the points that I like to make at this point, oops. So the 1.913, when we grab our calculator and start doing fraction exponents, we're going to start writing down approximations. The calculator is only going to tell us the approximation. When we write things in radical form, we can look at this and say this is what we call the exact value of the solution. So if we want to express the exact solution to x cubed equals 7, we often would write this with a radical. Usually we'll write our exact values with radicals. It's perfectly acceptable to say the exact value solution is 7 to the 1/3 power. But it's more common to write it in radical form. So usually we will use radical form for exact values. We'll usually use radical form for exact values. We could also use the fraction exponent form, but that's less common. We could say that the exact solution is 7 to the 1/3 power. But the more common way to read that would be to read that as the cube root of 7. All right, so the inverse of an exponent is a reciprocal exponent. Radicals are fraction exponents. The index of the radical is the denominator of the exponent. Usually, we'll use radical form for exact values rather than the fraction exponent form. As soon as we start doing radicals on our calculator, unless we have a nice exact value, like the square root of 4 is 2, then we're looking at an approximation. Third thing on the list of things to remember about solving with exponents is that if the exponent in the equation has an even numerator, then we'll get 2 real solutions. If the exponent in the equation is even, if the numerator of the exponent in the equation is even, then the equation has 2 solutions, real solutions. So this is an extra thing that we have to remember about solving equations with exponents. If the numerator of the exponent in the equation is even, then the equation will have 2 real solutions. That is, if when you're solving, the exponent in your solution has an even denominator, then we'll have two solutions. We can see why this is because even exponents make negatives positive. Even exponents turn negatives positive. Even exponents turn negatives positive. So if I have 2 squared, that's going to give me 4, but also negative 2 squared is a negative times a negative, and that's a positive. An even power of a negative number is positive. Even exponents turn negatives positive. Even exponents don't respect negatives, and they try to make them all positive. And so this is where the two real solutions are going to come from. So if we're solving an equation, where the numerator of the exponent in the equation is even, we know we're going to have two real solutions. So for example, if I want to solve x to the 6th is equal to 24, we notice that the exponent in the equation is even. That tells us we're going to have two real solutions. That's what we want to notice right away. We want to know what we're going to be up against before we're up against it. So the exponent in the equation is even. Therefore, we're going to have two real solutions. When we undo the even exponents, that's when the two solutions show up, one positive and one negative. So here we'll have x equals, well, let's do 24 to the 1/6 power. And we're going to write down the two solutions. So 24 to the 1/6 power is going to be 1.698. So we'll get two, 1.698 and negative 1.698. So 1.698 and negative 1.698. Those are both the real numbers. That when we raise them to the 6th power, we get 24. So if we check, if we take 1.698 to the 6th power, we'll get 24. And if we take negative 1.698 to the 6th power, we'll get 24 as well, because we're raising a negative number to a 6th power, an even power. So the even power will make the negative positive. So if the numerator of the exponent in the equation is even, then the equation will have two real solutions. So this is even if we start with a fraction exponent, it's if the numerator of the fraction exponent in the equation is even, then we'll also have two solutions. So if I had x to the 2/3 is equal to 24, we solve with a reciprocal exponent. So say x is equal to 24 to the 3/2. And we'll grab our calculator for the value, but we'll notice that the numerator of the exponent in the equation is even, so we're going to get two solutions. So if we take 24 and raise that to the 3/2 power, we get 117.576, we'll call it. But we'll also get the negative 117.576. This happens because we have x to the 2/3, and we see that the numerator of the exponents in the equation is even. And so that's why we get two solutions. If we look at this in radical form, then the exponent that's not part of the index, the part of the exponent, the numerator, is going to be the exponent under the radical. So in radical form, we see this as the denominator is the index, so this is the cube root of x squared. And so the exponent is even. X squared is going to have two solutions in an equation. So we can summarize that by just saying if the numerator of the exponent in the equation is even, then we're going to end up with two solutions, one positive, or we're going to end up with two solutions. The plus and minus happens when we undo the even exponents. The plus and minus happens when we undo the even exponent. Oops. So we split to two solutions when we undo the even exponent, which may mean that we have to do more things, any additional operations to both of the solutions. So this requires that we read the equation to find out when this happens. So if I write the equation x to the 2/3 plus 10 is equal to 24. If we look at the things that happen in this equation, if we read what happens in this equation first, to turn x into a 24, the first thing that happens is we raise to the 2/3 power. And the second thing that happens is we add 10. So here we are reading the expression. So our plan for solving to do inverse operations in reverse order to turn 24 back into x so we can find it, first, we're going to subtract 10, and second, we're going to raise to the 3/2 power. When we raise to the 3/2 power, that's when the two solutions will show up, because that's when we undo the even exponent. So on our calculator, we'll do a 24 minus 10 first, and that'll give us a 14. And then the second step is to say 14 to the 3/2 power. So I do 24 minus 10 first, and then I would take 14 to the 3/2 power. And this is where the two solutions should show up. We just punched a negative x, we just punched an even number as the denominator of an exponent on our calculator. And so that's where we're going to get two solutions, 52.383 and negative 52.383. Since that was the end, that was the last operation we needed to undo, those are our two solutions, 52.383 and negative 52.383. So our two solutions are just those, 52.383 and negative 52.383. We should compare this if the 2/3 exponent and the plus 10 happen in the other order. So for example, if I have an equation that says x plus 10, then raise to the 2/3 power, and that still equals 24, x turns into 24 in the different order. So we have to keep track of when the plus and minus part will show up. First, we add 10, and second, we raise to the 2/3 power in this equation. So our plan for solving, to turn 24 back into an x, first, we raise to the 3/2 power, and that's when our two solutions are going to show up, when we undo the even numerated exponent. And then second, we subtract 10, the inverse of adding 10. So we grab our calculator, we take the 24, we raise to the 3/2 power, and that gives us our two solutions, 117.576 and negative 117.576. Got two solutions. I got one positive and one negative. And the plus and minus happens when we undo the even numerator exponent. Now I've got to do this minus 10 operation to both of these solutions. So I got to take 117.576 and subtract 10 to get 107.576. Start off a little heavy metal 5 there. And I've also got to do to the negative 117.576. Negative 117.576 minus 10 is negative 127.576. So those are the two solutions. So x equals 107.576 and negative 127.576. So the plus minus happens when we undo the even numerator exponent. That may mean we have to perform additional operations on two different solutions. Any questions? Great. So we just want to keep adding to this. And one of the things that we want to add to this is negative exponents. We've had integer exponents. We know and we've had fraction exponents. The thing that we haven't encountered is negative exponents. So let's talk about negative exponents. So I'm going to start, since it's Friday, we're just going to go directly to the conclusion. We're just going to write down what to do with a negative exponent, and then we'll think about why that is as we do some problems. So if we have a negative exponent, if I see an expression, an equation that has an x to the -3 in it, what this means is 1 over x to the third. A negative exponent in the numerator is a positive exponent in the denominator. Also, if I see a denominator with a negative exponent, 1 over x to the -5, a negative exponent in the denominator is a positive exponent in the numerator. This is what we mean when we write negative exponents. So this might be new to some of you, and that's okay. It's secretly not new, but it might be a new thing for you, but secretly it's not really. So negative exponents move things from the top to the bottom or from the bottom to the top. Negative exponents move a numerator to the denominator or a denominator to the numerator. One thing that we have to be very careful about is we have to notice that the exponent only applies to what it's attached to. So if I have an expression that says, say, 2x to the -3, the -3 only applies to the x. If I want the -3 to apply to the product 2 times x, I have to use parentheses. In this expression, the -3 only applies to the x. So if I want to simplify that negative exponents, only the x of the third moves to the denominator. If I want the 2 to be included in all this business, I have to write it differently. I have to write 2x all to the -3. Then that would mean to move the whole thing down to the denominator. Where we could simplify it and we would have 1 over 8x to the third. The reason that I need to point this out is think back to the quiz X that we have, where I had the expression had 2x divided by 3y. And the most common thing to happen was that the 3y was one thing. And we were all okay with it. Even most of my colleagues would have read that the same way. We would just taken the order of operations, that PEMDAS, which is trash, they've taken that PEMDAS and thrown it out the window, 3y gets tokenized. In here, we wouldn't. The same people that are like, oh, 3y is one thing, would look at 2x to the -3 and say, oh, no, the x to the -3 is in the denominator, but not the 2. And I'm like, oh, dude, if you're going to have a rule, then have a rule. It's a bad rule if sometimes you follow it and sometimes you don't. So take PEMDAS and throw it out. And remember that context matters and your audience matters. So I want to point out that when we have negative exponents, when we read 2x to the -3, this is separate. The -3 is getting the negative x, sorry, the x is getting the -3 exponent, not the 2. The 2 stays behind. If I want the 2 involved in the -3 exponent, I need to put parentheses. This is not actually weird, except for the fact that we have some fishy rules that we think we're applying consistently. Because no one would think that the 2 gets multiplied by the x first if I just wrote 2x to the third. It's 1, 2, and 3 x's. Everybody agrees that that's what happens. But if I put the slash before this, all of a sudden we put the whole 2x to the third in the denominator. And that PEMDAS just goes flying out the window. And it's like, come on, man. But this is how negative exponents work. This is not unusual because we're familiar with decimals. So we're familiar with these negative exponents already. If we think about what the digits in a number mean, we have a decimal point, and then we have, let's say, the thousands, and then the hundreds, and then the tens, and then the ones, and then the 1/10ths, and then the 1/100ths, and then the 1/1000ths. These are the places in a number, and here's where the decimal point would go. And these are all just powers of 10. This is 1,000 is a 10 to the third, 100 is a 10 squared, 10 is a 10 to the first, a 1 is a 10 to the 0 power. So we got 3, 2, 1, 0. I wonder where we're headed next. 10 to the -1, 10 to the -2, 10 to the -3, or 1/10th, 1/100th, 1/1000th. Oh, I had already written those, so ignore that. But we could write that as 1/10 squared, or 1/10 to the first, 1/10 to the second, 1/10 to the third. So we have encountered negative exponents before. We just might not have seen them expressed as negative exponents. This whole powers of 10 decimal system with the place value uses the negative exponent stuff. And in either case, they're still just exponents, and the inverse of an exponent is a reciprocal exponent. So if I want to solve an equation that has x to the -3, I just raise to the -1/3 power, because that's the reciprocal of -3. All right, this weekend you're going to be working on some quizzes that will have you reading expressions and then solving. Remember that writing down your reading of the expression and your plan for solving is optional. This is supposed to take place in your mind. Writing down what you're punching into the calculator is taking place on your calculator. What takes place on the paper, your report to me, should just be the solutions. The point of being in a math class is to not have to write down all this stuff. Show your calculator. If you need to write the stuff down, then write that down for practice. But understand that the goal is to not write all this down, not to spend all this time writing this stuff down, but to be able to understand and remember the process well enough that you can just grab the calculator and go. That is the goal. The goal of the math class is to not do so much math. Any questions? All right, that's going to be it for today. Everybody have a nice weekend. I'll see you on Monday, and thanks for playing.